so what we'll do is we'll kind of take it from the top. So what we're looking at is the gravitational potential of an extended body that's not a perfect sphere. So gravitational potential of an extended body. So the idea was that we have, instead of a perfect sphere, we have some peanut-shaped body, and we're going to be out here, say, orbiting or being attracted to it. And what we did was first of all, we put the origin at the center of mass, the origin of our coordinate system, and then we're going to put an R prime. So this vector here is R minus R prime. Whereas this one is the R measured from the origin. If we're far enough away from this thing, it looks like a point anyway. But as we get closer to it, we start to see that it's not just a point. So the potential energy, I'll just remind us, G M M, a little m out here, over R for a point mass. Okay. Potential energy for a point mass. So the potential is there's a minus sign there, minus G M over R. And this is this mass here, M. So our goal is now to do kind of an expansion. So this will be some repetition of this, that's okay. So again, these are the expressions for a point mass somewhere. Okay. But if you have an extended mass, you have to do an integral or a summation over all the points comprising this mass, and this is R prime, by the way. So. And so what we get is V of R is going to be equal to minus G integral dm prime. So I'm just integrating over all the masses that comprise capital M over the distance, which is always R minus R prime magnitude. So that's the logical expression. And we already used this when we did the rod. Remember, we did the potential of the rod on the x-axis. But now this is for a three-dimensional body. So what we want to do is an expansion. So next, expand. And I'll explain what kind of expansion. For R prime, much less than R. So we're supposed to be a sufficiently large distance away so that and I could even say this, suppose we've got a length that characterizes the size of that entire body, i.e. R much greater than L. So we're far enough away from the body, that's the whole point. Okay. Then we can do a systematic expansion in terms of R prime, because see the argument, the potential here is a function of R, and these R primes were integrated over. And this dm prime could be your density times d volume, something like that. Okay. Good, so we need to expand. And this is a pretty interesting expansion. A function of this form, f of R plus R prime in a Taylor series, that'll be f of R plus sum over df that's the quadratic term, and that's as far as that's going to happen. That's as far as we're going to take it. So, you know, this function, 1 over r minus r prime, that's where my plus r prime is my negative r prime. And so I just have a minus sign built in here, that'll be no problem. So we're going to have 1 over r minus r prime and be equal to 1 over r. That's a nice result there when r prime is 0. Plus sum over d dxi 1 over r minus xi, so all the minus sign built in there. Prime, sorry. And then I'll have plus 1/2 double sum d squared xi dxj of this 1 over r. Because this 1 over r, evaluated at 1 over r, is when we've taken the derivatives at r prime equals 0. And then xi prime, xj prime. And these two minus signs that are in here, minus signs minus cancels, okay, so we get a plus anyway. So that's what we have to do. So now we can do the derivatives of 1 over r. So now we have d dxi 1 over r is equal to minus 1 over r squared xi over r. So that we've done a couple times. Definitely want to practice that derivative. It comes from the gradient of r being x over r. Okay. I'll just change it. So you've got minus xi over r cubed. And then you do d squared dxj dxi. And now we're doing the derivative of this thing with respect to xj. So if I is equal to j, we get a 1. If I is not equal to j, we get a 0. So we get the negative product or delta ij times 1 over r cubed. And we see it's the product rule. And we get minus and a minus 3 plus 3 over r to the 4th xj over r. So this turns into 3. Oh, I had an xi in here when I held the xi constant. Okay, so 3 xi xj over r to the 5th minus r squared delta ij r to the 5th. So here I multiplied top and bottom by r squared. 1 over r to the 5th. Okay, so now we have to go with these results into this expansion here and see what happens. What's going to happen here? So, okay, I'm going to actually reproduce this so we have this in front of our eyes. So we've got minus g dm prime r minus r prime. Okay. And now we'll go ahead and fill in. So the first one we've got integral minus g dm prime, but that first term is just the 1 over r. 1 over r is not prime, so we can actually pull this out here. And what's the integral of dm prime over the entire body? That's just capital F. like the total mass. I'm going to go ahead and put that here as a useful comment. So this term is already minus Gm over R. That's the good old point mass property if you're far enough away from it. Okay. Now the second one, we're going to have minus G integral dn prime. And now we have to go ahead and plug this in here. You can see the minus signs are going to cancel, so I'll go ahead and cancel those right now. And then we'll have d dxi 1 over r. We'll have sum over minus xi over r cubed. Those are the derivatives. I equals 1 to 3. And then I have, actually, let's go ahead and we'll leave the negative g here, minus xi, and then I have minus xi prime. This one we're going to also deal with right away. Because what's interesting about this is we're integrating over the primes. So here, I'll look right underneath here. So this we could have minus, that's fine. We've got a minus sign out here. We could do a summation of these integrals e n prime. The r to the cubed could actually be pulled out front. That's I equals 1 to 3. So pull the r to the cubed out, these cancel. So we have xi prime if I place some parentheses here, put the xi there. I mentioned this the other day. This thing in parentheses is going to be equal to 0 if we have the origin and center of mass, and we do. So equals 0. And so this is a really important note here. Our center of mass is defined as sum of masses over the total mass. So it's equal to sum over m by r I over total m I. So that's the definition of the center of mass. Now, our body is, we're using the prime coordinates for the body. But you'll notice this integral is of that form, mass times, it's called moment, right? Mass times length. So this integral is just like the numerator, one of these numerators. Okay. Sum of m times x, in this case prime. That means that if we choose the center of the origin and center of mass, then all three of these are actually equal to 0. And we did choose the origin and center of mass because origin is at the center of mass. At the center of mass. And in electricity, this integral would not necessarily be 0 because we have two signs of charge. But in gravity, we just have positive mass. Therefore, this is 0 here. So good, this one's 0. So we have this, and we have this one being 0, and now we'll work on the third term. So yeah, make sure you have this note there. So if origin at center of mass, then last one we're going to do is this here, and this is the big one. I'm gonna have to erase some stuff. I'm gonna erase this note here, okay? So we can continue on there. Good. Okay, so now we have plus, and we've got negative G. I'll do this. That's fine. So we've got negative G. Write down the integral first. We've got 1/2 double sum ij. We go back over to there. 3xixj 1/5 minus r squared delta ij. Also over r to the 5th. And then xi prime, xj prime. So this one needs a bit of manipulation. Integral, and of course I have to have the dm prime in here somewhere. We've got minus g dm prime, so we're integrating over. So for the moment we got that right there, we're gonna fix that up. Okay, good, this is good to go. So we're looking at this thing here, and there are a couple of things going on. If we were to ignore this second part here, we'd just have 3xi xj xi prime xj prime with a complete double sum. So we can actually switch the unprimed and the primed quantities on that first integral and have changed nothing. In other words, if I prime these and have these unprimed, it'll be the same expression. But in fact, I can do that on the second one as well, because this r squared is only for the diagonals when I equals j. So this is x1 squared plus x2 squared plus x3 squared multiplied by x1 prime squared plus x2 prime squared plus x3 prime squared. So what I can do, and this makes the whole difference here, and I'll do a couple steps right away. I can turn this into 1/2 double sum. I pull that g out first. Yeah. So let's do this with the plus negative g. We can do 1/2 double sum I and j. We're just rearranging this. We've got the integral dm prime, and we're going to have 3xi prime xj prime minus r prime squared delta ij. And apparently I can pull the r to the 5th out front, which I'm going to do. But we're not integrating over the r to the 5th, so the 2 r to the 5th. Actually, I'm going to bring it back in there in a moment. Okay, so I just rearranged, but you have to note I was able to exchange the prime and the unprimed. Completely legitimate reasons. Note. Without changing the total sum. And this here is the form that we're actually going to work with. this here, this integral, this is called Qij, and there are 9 of them. It's a 3 by 3 matrix. We're going to see it simplify quite a bit. Okay, so before we go on, I'm going to ponder this for a moment. And yeah, what are we integrating over? We're integrating over that body that we started out with. And these are the coordinates of the body, because, you know, with the origin at the center of mass. So this Qij is called the quadrupole tensor. And these square matrices, which is what it is, matrix, these square matrices are very common, and we're going to calculate one of these before the hour is over. But we can now actually write down what we found. So what we have is minus G 1/2 double sum Ij Qij xij over r to the 5th. When all is said and done, that's the result we came out with. Quadrupole tensor. Next to the 5th, I brought back in there with 1/2. Yeah, so we have everything there. You can see dimensionally these things are masses times lengths squared, right? And then here you've got length squared over lengths to the 5th. So dimensionally the whole thing comes out as it has to, G mass over length. So this is all about the mass distribution. The other thing you can see is these are x squared terms, right? So x squared over x to the 5th. So again, these are 1 over x cubed terms, as advertised before. Good, so now we've done that expansion, this exchange of the primes and unprimes is really important, so you can study that if you're interested. And now we want to implement this thing. Okay, this is good. It's going to be put in a box. So here we have, this is what we have found. And you can see the first term, that's the point mass property. So you've got an extended body, you're far enough away from it, these things vanish. If you're far enough away, they get more and more negligible, and you're left with the point mass potential. But if you're closer to it, then the shape of the body plays a role. It seems to be pretty complicated, but we'll see the basic cases are easy to deal with. So that's the quadrupole tensor, and I'm going to write that down here. And then we have some board there to the right to study it. So Qij equals integral dm prime 3xi or prime squared delta ij. Quadrupole tensor integrated over the body. And of course the body has to have its origin at the center of mass. So what I'm going to show you next is this 3 by 3 matrix is not that complicated. And then, so most of the cases we're only going to have to calculate one contribution at most 2. And when we study this thing, we can leave off the primes and just under the understanding that we're integrating over that body. Let's see if we can tie all this stuff together. Okay, so there's our expression here. So the first point that's very interesting, so properties of Qij, quadrupole tensor. And the first property is that it's symmetric. Right, if I substitute I for J, this isn't a J by the way, still get the same result, right? So a symmetric matrix is always nice. So symmetric. The next property is that some of the diagonals. Anybody stare at that thing and figure out what the sum of the diagonals is? Isn't that a little problem? If you add up all 3 of these, 1, 1, 2, 2, and 3, 3. If you add them up, this r prime squared, see the diagonals are the only time that this r prime squared plays a role. So if you add them up, you'll get 3x1 squared minus x1 squared plus x. Here, let's just kind of do this. So we get, I'll just put this here as a note. You get 3x1 squared minus x1 squared plus x2 squared plus x3 squared. And I'm dropping the primes. We're integrating on the body. And then we do the second one plus 3x2 squared minus plus 3x3 squared minus. Okay, now I'm going to stand back and let you guys declare the answer there.
0, right?
0. Yeah. So because you had 3x1 squared, 3x2 squared, 3x3 squared, and you subtract that sum off 3 times. So that equals 0. And the third property, I'll just put here as a little phrase, if your body is symmetric, the off diagonals are all 0. So the off diagonal elements vanish. If you have a symmetric body. And maybe a little picture would show that. See, the off diagonals, delta ij is 0. So I'll just give an example. So suppose you had integral dm prime 3, forget the primes, okay, 3x1, x2. That's an example of an off diagonal of this thing where the delta ij is equal to 0. Okay. Well, if it's a symmetric body, your origin is at the center of mass, then you've got just as much x1 on one side as on the other. They have a symmetric body. It's a disk. Okay. x1 and x2. You can pull the, you can imagine pulling the x2 out of the integral and integrating over x1 one side to the other, and you're going to have a 0. Okay. So symmetric bodies, the off diagonals vanish. Now, if the off diagonals vanish, then you're looking at a very basic thing. Now I'll just put this up here. Now you're looking at Qij equals Q11 now you see you have to do at most 3 for a symmetric body. We're going to be interested in symmetric bodies, okay? 3 integrals, that's not bad. The sum of these 3 equals 0, so you only have to do 2. Okay? And if the body's symmetric enough, 2 of these will actually be equal to each other, and then you're reduced down to a single integral, which is the way we're going to treat most of our problems. Okay? So, yeah, this turns out to be pretty easy to deal with after all. We didn't have any homeworks left over. We just had the rework on the exam, right? So we have plenty to do. But one problem we're going to do, maybe I'll do it here, is the quadrupole tensor of that original rod of length L that we did the other day. Okay? And we'll be able to touch it on touch base with our old results. Okay. So these properties here, that it's symmetric, that the sum of the diagonal elements, that's also called the trace. The trace of the matrix, just so you know. Equals 0, and the fact that octagons vanish for a symmetric body means that you don't have many integrals to do. Okay? That makes it simple. Then we can write out the whole thing and start to see its structure. Now here's a really interesting point. I haven't done it this way before, but you know, we haven't yet proven mathematically, although we mentioned it a lot, that a spherically symmetric body attracts like a point of mass, right? We've mentioned that many times. If we had proven that already, then we can just state with certainty that for a spherically symmetric body, all these integrals vanish identically. Right? But what we'll do, yeah.
Wouldn't it need to be spherically symmetric with uniform density?
Good question. It doesn't have to have uniform density, but the density itself has to have spherical symmetry.
Okay.
And then it acts as a point mass. Yeah. So we're going to turn things around this time, and I'm going to have you guys, we'll get started on it together, show that for a spherically symmetric mass distribution, these things vanish identically. And we can take that as part of the proof that this spherically symmetric mass distribution attracts as a point mass. That's kind of a different approach to it. Because we got this term out here up front, right? It came from taking the origin at center of mass. So let's see, we got a lot to do here. I'm going to leave these up. I'm going to erase these and get started on this stuff. I'll put a couple of these up as homework. We'll probably end up working it together, but I'll just write them up here as problems. So the first one, this is the most important one actually. Calculate quadrupole tensor for this good old mass distribution, x1, x2, right? We have the linear mass distribution from minus element 2 to plus element 2. We call this x and y, now it's going to be x1 and x2 axis, right? So when we calculate this and plug it into here, we should get back our formulas that we did with those Taylor expansions. This is going to be a nice one. And you'll see, of course, this is a very basic and easy one. For then compare B of R to the expansion for B of X that we did earlier. That's enough of a hint. I hope to tackle these with you guys together. Okay. You guys remember what I'm talking about? We had done the simple integral for b of x and b of y, and then we did an expansion of those natural logarithms. And we got some results with 1 over x cubed. And we have to get them back here too. Okay. And another homework is calculate Uij for the spherically symmetric mass distribution. And I'll characterize that. Remember, we're dropping the primes when we actually do the integrals, okay? We're dropping the primes. So the spherical symmetric mass distribution is dm prime. It's the mass density, it's the mass element, so it's the total mass divided by 4/3 pi radius cubed. Actually, no. So what we're going to do is we have rho of r d volume. I'm just going to write d3r for a moment. What we're going to do here is get the volume element using spherical polar coordinates. The key to this one is spherical polar coordinates. Use spherical polar coordinates. Who remembers spherical polar coordinates? Done a little bit up here and there.
That's the one where you have radius and then 2 angles, right?
Yes, radius and 2 angles. Anybody remember the volume element? We'll look it up. Those are kind of automatic. They're good. Okay. Use spherical polar coordinates. And because it's a sphere, it's going to suffice to do just one of those. When we have that diagonal, there are 3 of them. If we do one of them, it's good enough, right? Because we can just exchange coordinates. So calculate 1 of the Uij's on the diagonal. And what's going to happen is it's going to equal 0. Like I said, all that work just to prove that it's 0. Because none of that from the outset. But it's very instructive. Because we'll take that as the proof of the point mass nature of the extended body. It's very specific. But yeah. Oh, so I got to drop the primes here, right? I'm dropping the primes because we don't need them. We needed them for the derivation, but once we just know we're integrating them. Okay, let's see here. That'll be a good one. So we have 3r squared sine theta theta dt. So that's the volume element. Anybody remember that one? Yeah. Okay. So when we do this integral, it's a bit of a mess, you know. It's going to be one of the diagonals. So for example, Q11 for this problem, we have integral rho of r squared sine theta dr d theta d phi. And then what? Then we would have this times 3 x1 3 x1 squared x1 squared plus x2 squared plus x3 squared. And x1, x2, x3 are going to be those spherical polar coordinates. So yeah, you know, we'll probably work on that one together, but that'll get it started. Point is, and you know, these are gonna be proportional to R, you're gonna have the R squared in there as well. A bunch of signs and cosines and what have you. The integrals come out to be 0. Okay, we'll work on those together because we have a little more time. So I'm just setting these up. This one here, maybe we should have done this one from the outset, but I wanted to give the big picture. The big picture now, this is what I'll end with, is that if you have a spherical symmetric mass distribution, you're back to 1 over R, and that's what Isaac Newton used when he had Earth and Moon and planets and stuff. The assumption was that it in fact it was a point mass. You know, Newton already was aware of the moons orbiting Jupiter. And definitely a moon close to Jupiter, it better be seeing Jupiter as a point mass. Because it's pretty close, it's a hugely extended body. The other big picture aspect here is the next term is clearly 1 over R cubed. Right? If you've got R, you know, x squared over x to the 5th, so you have 1 over x cubed. So the next term that we found earlier on this guy here, 1 over x cubed, the very generic, right? That's the next term. The quadratic one's 1 over R squared, don't exist. Good, so I'd say we have everything set up now. So we'll tackle some of this stuff next time. Oh, and what motivated all this was when we did the apsidal anglum, we had that 1 over R cubed, remember that beta over R cubed in the potential energy. So that's going to take a full circle of that and justify all of those assumptions that we made. Good.